So today I'm presenting our study investigating anisotropy in the angular distribution of solar wind sputtered atoms. My name is Ben Clouter-Gergen, and I'm presenting on behalf of Memorial University. Next. So first, what is solar wind sputtering? The solar wind is an energetic ion stream released from the sun, which traverses through space and can bombard planetary surfaces, such as those of the moon and Mercury, ejecting surface atoms and potentially modifying the surface compositions of planets and contributing to the formation of their exospheres. Next. So the knowledge gap we've identified here is that there's a limited ability to isolate the contributions of exosphere maintaining sources, and so quantification of these sources is in need. So for planetary relevant cases, the sputtering yield has been well studied, but how atoms are angularly distributed when sputtered from a planetary surface, that's been given far less attention. Next. So precisely our focus is on quantifying anisotropy for the complete angular distribution of ejecta. Similar cases have been considered, but they've only looked at sputtering in the incidence plane. We then move on to explaining the physics underlying the observed anisotropies, and we do this by distinguishing between the sources of ejected atoms. Next. So we simulated sputtering using the software SDTRIMSP, which follows the binary collision approximation model. For impactors, we looked at 1 keV hydrogen, which is approximately 96% of the solar wind, and 4 keV helium, which is approximately 4%. We also consider an experimental case, 20 keV krypton, which is commonly used to get a more abundant sputtering yield, but whose angular distribution may be discrepant with these solar wind-like cases. And so seeing whether there are differences may be important for experimentalists looking to scale their results in making inferences to planetary science models and observations. And then for all impactors, we bombarded a silicon dioxide substrate. It's a mineral readily present in both the surfaces of the moon and Mercury. Next. So depicted here is the scenario and coordinate system. The situation involves an incident atom at an angle between 0 and 70 degrees impacting a target substrate and sputtering atoms as a function of polar and azimuthal angles ranging from 0 to 90 and 0 to 180 degrees respectively. Next. So first we quantify for backward anisotropy. So shown on the y-axis, we've taken the forward sputtering yield relative to the total yield and expressed it as a percentage and function of incidence angle. And then shown in the top right here, so the forward sputtering yield is defined as any ejecta occurring in that shaded region, which occurs from 0 to 90 degrees polarly and 0 to 90 azimuthally. So you can see at an impactor incidence angle of 0 degrees, 50% of atoms are sputtered forward in all cases. As the impactor's incidence angle is increased, forward sputtering percentages increase in all cases. Click. So between 0 and 30 degrees, forward sputtering percentages are similar in all cases. Click. And then between 30 and 70 degrees, we can see that the forward sputtering percentage is greatest for the hydrogen on silicon dioxide case, while kind of leveling off for helium and krypton. Next. So we look to understand the observed anisotropies by breaking things down into 4 ejection mechanisms contributing to the total sputtering yield. The first involves an incident atom entering material and directly ejecting a surface atom, which is termed an ion-in primary knock-on atom. Next. The second involves an incident atom entering the substrate, impacting a surface atom, and that atom going on to impact another atom, and then potentially another atom, and eventually an atom's ejected, which is termed an ion-in secondary knock-on atom. Next. The third involves an incident atom entering a target substrate, being reflected, and eventually impacting a surface atom on its way out of the material, and that atom is termed an ion-out primary knock-on atom. Next. And then finally, we have an incident atom which enters a target substrate, is reflected, impacts a surface atom, and then that surface atom goes on to impact one or more other surface atoms prior to the ejection of what's termed an ion-out secondary knock-on atom. Next. So we can decompose the observed forward sputtering percentages as follows. Click. Shown here, we have the forward sputtering percentage change. Click. And it can be if you take for each ejection mechanism, click, the effect of a change in its contribution to the total sputtering yield plus, click, the effect of its a change in the degree to which that mechanism is sputtered forward, you can get the overall forward sputtering percentage change. Click. So first, for 1 keV hydrogen on silicon dioxide, click. Looking first at ejection mechanism contributions, we plotted the yield for a given ejection mechanism relative to the total yield as a function of incidence angle. And we can see that as you increase the incidence angle, there's a shift from ion out ejecta being predominant to ion in ejecta being a bigger part of the overall sputtering profile. Next. Then for ejection mechanism forward sputtering percentages, we've taken the forward sputtering yield for a given mechanism relative to the total yield for that mechanism. And we can see that as a function of incidence angle, ion in primary knock-in atoms are sputtered forward at the highest rate, followed by ion in secondary knock-in atoms, and then the ion out ejecta, which are sputtered nearly isotropically. Next. So in green, we have the effect of ejection mechanism contributions. In blue, that's the effect of ejection mechanism forward sputtering percentages. And so both of these factors influence what's shown in red, which is the overall forward sputtering percentage. And so between the 0 and 30 degree range, you can see that the blue curve increases while the green curve doesn't increase as much. So initially, what's driving the overall forward sputtering percentage change is that the ejection mechanism forward sputtering, for each ejection mechanism, forward sputtering percentages are increasing. Beyond the 30 degree mark, however, the green curve catches up to the blue, and here ejection mechanism contribution changes have more of an effect as there's a shift, an accelerating shift from ion out ejecta to ion in ejecta, and that's why the overall forward sputtering percentage in this case is able to continue increasing linearly like it does. Next. So for 4 keV helium on silicon dioxide, there's a slight increase in the percentage of ion in pKa's in the total yield profile. Next. We can see that again, ion in primary knock-in atoms are the main contributor to the total yield, have the greatest forward sputtering percentage, followed by ion in secondary knock-in atoms, and then ion out ejecta being sputtered almost isotropically. Next.
2 minutes.
Good. And so then you can see in this case, the blue curve increases again rapidly, while the green curve, which is the effect of ejection mechanism contributions, doesn't increase much at all. And then again, looking beyond the 30 degree mark, there's very little change in that green curve this time. And this differs from the hydrogen case, where ejection mechanism contributions had a big effect in changing the overall percentage of atoms sputtered forward. And that's why you're seeing the overall percentage of atoms sputtered forward, the red curve, leveling off. Next. So yeah, for the krypton and silicon dioxide case, similar. You get a change in the percentage of ion in SKA, a decrease in ion in SKA sputtered forward. Next. Again, ion in pKa's are the leading mechanism. Next. And again, we see that ejection mechanism contribution changes, unlike the hydrogen case, never really become an effect that influences the overall forward sputtering percentage much at all. Next. So in summary, we found that forward-backward anisotropies are initially similar in all cases, and this is the result of the effect of ejection mechanism contribution changes being minimal, but ejection mechanism forward sputtering percentage changes driving these anisotropies. Then for the case of hydrogen and silicon dioxide, we found that at larger incidence angles, the overall percentage of atoms sputtered forward continued to increase linearly, and that this was driven by an increase in the effect of ejection mechanism contribution changes. Next. And so the implications of our work, so we quantified ejecta angular distributions for solar wind-like cases. These can be used as inputs into global and granular ejection models. And then experiments which employ increased mass and energy impactors, they're likely underestimating the degree to which ejecta angular distributions are forward pronounced, given for krypton on silicon dioxide, the forward-backward anisotropy was much more similar to the helium case rather than the hydrogen case, and hydrogen is the primary component in the solar wind. Next. Thank you.